at the latest since the Nobel Prize in Physics was awarded for research on graphene in 2010. 2D materials, nanosheets with atomic thickness, have been a hot topic in science. This significant interest is due to their outstanding properties, which have enormous potential for a wide variety of applications. For instance, combined with optical fibers, 2D materials can enable novel applications in the areas of sensors, nonlinear optics, and quantum technologies. However, combining these two components has so far been very laborious. Typically, the atomically thin layers had to be produced separately before being transferred by hand onto the optical fiber. Together with Australian colleagues, Jena researchers have now succeeded for the first time in growing 2D materials directly on optical fibers. This approach significantly facilitates manufacturing of such hybrids. The results of the study were reported recently in the Journal on Materials Science Advanced Materials. Growth through a technologically relevant procedure, we integrated transition metal dichalcogenides, a 2D material with excellent optical and photonic properties, which, for example, interacts strongly with light, into specially developed glass fibers, explains Dr. Falk Eilenberger of the Uni. Unlike in the past, we did not apply the half-nanometre-thick sheet manually, but grew it directly on the fiber, says Eilenberger, a specialist in the field of nanophotonics. This improvement means that the 2D material can be integrated into the fiber more easily and on a large scale. We were also able to show that the light in the glass fiber strongly interacts with its coating. The step to a practical application for the intelligent nanomaterial thus created is no longer very far away. The success has been achieved thanks to a growth process developed at the Institute of Physical Chemistry of the University of Jena, which overcomes previous hurdles. By analyzing and controlling the growth parameters, we identified the conditions at which the 2D material can directly grow in the fibers, says Jena 2D materials expert Professor Andrei Turkinen, explaining the method based on chemical vapor deposition (CVD) techniques. Among other things, a temperature of over 700 degrees Celsius is necessary for the 2D material growth. Hybrid material platform. Despite this high temperature, the optical fibers can be used for the direct CVD growth. The pure quartz glass that serves as the substrate withstands the high temperatures extremely well. It is heat resistant up to 2000 degrees Celsius, says Professor Marcus A. Schmidt of the Leibniz Institute of Photonic Technology, who developed the fibers. Their small diameter and flexibility enable a variety of applications, adds Schmidt, who also holds an endowed professorship for fiber optics at the University of Jena. The combination of 2D material and glass fiber has thus created an intelligent material platform that combines the best of both worlds. Due to the functionalization of the glass fiber with the 2D material, the interaction length between light and material has now been significantly increased, says Dr. Anthony George, who is developing the manufacturing method for the novel 2D materials together with Turkinen. Sensors and nonlinear light converters. The team envisages potential applications for the newly developed materials system in two particular areas. Firstly, the materials combination is very promising for sensor technology. It could be used, for example, to detect low concentrations of gases. To this end, a green light sent through the fiber picks up information from the environment at the fiber areas functionalized with the 2D material. As external influences change the fluorescent properties of the 2D material, the light changes color and returns to a measuring device as red light. Since the fibers are very fine, sensors based on this technology might also be suitable for applications in biotechnology or medicine. Secondly, such a system could also be used as a nonlinear light converter. Due to its nonlinear properties, the hybrid optical fiber can be employed to convert a monochromatic laser light into white light for spectroscopy applications in biology and chemistry. The Jena researchers also envisage applications in the areas of quantum electronics and quantum communication. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.